Catalysis. The third chapter, third part of this chapter is said to be colloids. It is said to be colloids. So already we have finished the concept of adsorption. So now we need to study something about catalysis. So yesterday already we have started the concept of catalysis. Then the last part of this chapter would be colloids. Yesterday we have started with this concept of catalysis. Under the concept of catalysis, we have studied that why a catalyst is required, why should we use a catalyst, and we have studied first the definition of a catalyst, what is a catalyst, then why should we use it, why should we use catalyst. Yesterday you have studied that there will be certain reactions which are said to be very fast. So this will not require any sort of catalyst. And there are certain reactions which is happening very slowly, The reactions which occurs very slowly, so in order to do it at a faster rate, in order to get the product at a less time, we should use certain substances which is called as a catalyst. For fast reactions, yesterday I have given you some ionic reactions. Generally ionic reactions occurs at a faster rate and it does not require any sort of catalyst. Very slow reactions, for example rusting of iron, these are very slow reactions, rusting of iron, or there may be any molecular reactions, breaking and making of covalent bonds, molecular reactions which happens very slowly. In order to catalyze these reactions, we need to use certain substances called as catalyst. So this catalyst would not be consumed during a reaction, its mass would be remaining same. So what amount of the catalyst that we have taken before the reaction, even at the end of the reaction the mass of the catalyst remains same. I think this point is clear, students. Yesterday I gave you the example of potassium chlorate 2KClO3. So when I heat it, so this would be converted into 2KCl plus 3O2 gas. This is called as decomposition of potassium chlorate. Suppose if I don't use any catalyst, for the completion of this reaction, it may take nearly 4 hours. Now, if I use the catalyst like MnO2, solid, this MnO2 solid will not be consumed during a reaction. It is not a reactant, it is not a product, and we call such a substance as catalyst. This is called as a catalyst. I think this point is clear, students. So yesterday we have finished this part. Then after describing all these things, we have also explained what is the definition of a catalyst. So that is what we have studied in our yesterday class. So what is said to be a catalyst? Tell me, students, what is the definition of a catalyst? So a catalyst is a substance. Yesterday we have seen that. What is that catalyst? A catalyst is a substance when added to a reacting system increases the rate of a chemical reaction. Without changing itself or being consumed. So this is important, which increases the rate of a chemical reaction. Is it clear, students? Then after this we have studied what is catalysis. We have studied the definition of catalysis. So tell me, students, what is the definition of catalysis? The phenomenon of increasing the rate of the reaction, the phenomenon of increasing the rate of the chemical reaction, rate of chemical reaction with the help of catalyst, with the help of catalyst, with the help of catalyst, with the help of catalyst is known as catalysis, is known as catalysis, is known as catalysis. Is it clear, students? Yesterday we have studied even this concept also. Then we have classified what are the types of catalysis reactions. So the types of catalysis reactions are said to be of two types. So depending upon the catalyst and the reaction mixture, yesterday we have studied types of catalysis. Types of catalysis. Tell me, students, what all things you have studied yesterday under types of catalysis. Depending upon the phase of the reaction medium and the catalyst, so we have divided this into two categories. So the two classifications are said to be, one is said to be homogeneous catalysis, one is said to be homogeneous catalysis, another one is said to be heterogeneous catalysis. Heterogeneous catalysis. So tell me, students, what is homogeneous catalysis? Yesterday I have studied, if the reactants, products and catalyst, if the reactants, products and catalyst, all of them are in the same phase, then we call it as homogeneous catalysis. Then we have studied, if the reactants and catalyst are in different phases, then we call it as heterogeneous catalysis. This is what you have studied in your yesterday's class. Then we have given the examples. I told you definition of homogeneous catalysis, definition of heterogeneous catalysis, definition of examples of homogeneous catalysis and heterogeneous catalysis. All these are said to be important. After studying these many things, so I think yesterday we have differentiated between differences between homogeneous catalysis and heterogeneous catalysis. Even that part is also over. Did we study about that, students? No. So what we have studied is only up to the examples of heterogeneous catalysis. Today let us study something about the mechanism of heterogeneous catalysis. Mechanism of heterogeneous catalysis. Tell me, students, what is heterogeneous catalysis? What do you mean by heterogeneous catalysis? Catalyst and reactants are in different phases. Catalyst and reactants, these are in different phase. These are in different phases. These are in different phases. I think this point is clear, students. Now let us study how the mechanism of heterogeneous catalysis takes place. Usually for heterogeneous catalysis, catalyst will be solid. Catalyst will be a solid. Reactants will be gases. Generally it will be gases. I think this point is clear, students. The mechanism of heterogeneous catalysis takes place in 5 steps. It takes place in 5 simple steps. So let me explain you each and every step. So I'll explain in the form of diagram, students. So let me say that this is said to be the surface of a solid catalyst. Let me say this is said to be a catalyst. This is said to be the catalyst. Due to the presence of free valencies on the surface molecules of the catalyst, it shows catalytic property. Now let me say that the two reactants that are coming, let me say like this, the two reactants that are coming, this is A and this is B. So let me say that the two reactants are coming, which is coming and diffusing into the part. So we call the first step as the diffusion of the molecules of the reactants to the surface of a catalyst. What is this step, students? So these are called as what? Reactants. These are called as reactants. Reactants diffuses into the surface of the catalyst. So what do we call the first step as? Diffusion. diffusion of molecules, diffusion of molecules, diffusion of molecules to the surface, to the surface of catalyst. This is the first step, to the surface of catalyst. Once if the molecules start diffusing into the surface of the catalyst, in the second step, let me say that there will be adsorption. Let me show, this is said to be a catalyst. Let me say this is said to be a solid catalyst. Onto the surface of this catalyst, the two reactants what we have taken will come and get attached. So we call this attachment is because of the force of attraction between the catalyst and the reactant molecules. So we call this step as adsorption of reactants. We call this as adsorption of reactant molecules, adsorption of reactant molecules on the surface of catalyst, on the surface of catalyst. Is this point clear, students? On the surface of catalyst. Now once if the catalyst gives the surface for the reactant molecules, so there would be formation of intermediate on the surface of the catalyst. And let me say step number 3, what happens in step number 3? Now let me say that if this is said to be the surface of a catalyst, once if the reactant molecules gets attached, it provides a scope for the reactant molecules to form the intermediate, and it is leading to the formation of products. Let me say that the big one what I have written now, so this is coming nearer. Once if it is adsorbed on the surface of the catalyst, then there would be scope for the interaction between these two reactants and it forms an intermediate. Via the formation of an intermediate, it forms the product. So therefore I should say in step number 3, what is happening, students? Tell me. Occurrence of chemical reaction, occurrence of chemical reaction, occurrence of chemical reaction on catalyst surface, on catalyst surface, on catalyst surface through the formation of an intermediate, through the formation of an intermediate, and finally it forms the product. Once if the product is formed on the surface of the catalyst, then what should be the fourth step, students? So the fourth step should be the disruption, means the product which has been formed that has to go out. Let me say this is said to be the catalyst surface. Now once if this product is being formed on the surface of a catalyst, it has to start living. See here it is touching to the surface of the catalyst to give scope for the further reactions. Once if the product is formed, it has to be moving away. So let me say that step number 4 will be disruption. Disruption means what? Dislodging of the product from the surface of the catalyst. Disruption of products. Disruption of products. Disruption of products. Is it clear, students? Once if the product is disrupted, then what should happen? Diffusion back. Diffusion back means it is moving away. So let me say that in step number 5, so whatever the product has been formed, that has to go away. Let me say that this is moving away, this is going out. So the product which has been formed, which is moving away, so that it is giving scope for the further reaction. Is it clear, students? So now what is that step number 5? Step number 5 is diffusion back. Diffusion back. What is that diffusion back means? Diffusion back of the product formed from the surface of the catalyst. Once it gets disrupted, then it has to move away so that it makes the catalyst surface free for the further reactant molecules to come and so as to give back the products. I think, students, the point is very clear. We have studied about the mechanism of heterogeneous catalysis. Heterogeneous catalysis means catalyst and the reactants are in different phases. Usually for heterogeneous catalysis, catalyst is said to be a solid and reactant is said to be the gas. The mechanism of heterogeneous catalysis takes place in 5 steps. Step number 1 would be diffusion of molecules to the surface of the catalyst. You can see if this is the surface of a catalyst, the reactants A and B are coming and diffusing onto the surface. Once if they come and get absorbed, so in step number 2 there would be scope for chemical reactions because of the free valencies of the catalyst, it gets attached to the free valencies. So chemical bond would be formed, and that bond form should not be too strong or it should not be too weak, so that it should be of appropriate strength. If it is too strong, so the molecules which has been absorbed, so would be not living back, so that there would be no scope for the further reactions. Okay, what is step number 2? Adsorption of reactant molecules on the surface of the catalyst. What is step number 3, students? Occurrence of chemical reactions on the surface of the catalyst, so that via the formation of intermediate a product is being formed. Occurrence of chemical reaction on the catalyst surface through the formation of an intermediate. Is this point clear? In step number 4, the formed product has to be disrobed from the surface of the catalyst. So once if it has to be disrobed, then we have to say that diffusion back, whatever product has been formed has to leave the catalyst surface and it has to be made free, so that the cycle can repeat. Once again remaining reactant molecules can come and the cycle continues. So this is called as the mechanism of heterogeneous catalysis. Is this clear, students? Let me show you what is that diagram given in your NCERT, so that will not be asked for your examination, but you need to remember what are the number of steps, what all happens in each and every step. Up to now it is not asked in the annual examination. So I'll erase it, students. Let me show you what is that diagram that is given in your NCERT. You can also refer this diagram from the NCERT book also, students. See, this is the diagram given. So you can refer in your NCERT book. So this is given in page number 132 in your NCERT book. It is given in page number 132. Just refer this, students. Is it clear, students, now? Shall we go for the next part? So you can refer this diagram in your NCERT book. It is given in your NCERT book. I'll explain it, students. See once. See, this is said to be a catalyst. Since it is not bonded to any of the things, we call this as free valencies. Catalyst surface having free valencies means it has not been attached to anything. A and B are the reacting molecules. It would come and it would be adsorbed onto the surface of the catalyst. Adsorption of reacting molecules takes place. Once if the adsorption takes place, then we say that there would be formation of intermediate AB. We call this as an intermediate. Now we can see catalyst A, B and a catalyst valency has been attached. What do we call this as? Intermediate. Once if this is formed, disruption, so AB is removed away and the product is diffused back. It has to be dislodged. We call it as disruption, and the catalyst is regenerated and the cycle can continue. This is the diagram given in your NCERT book. Is it clear, students? Shall we go for the next part? This diagram is given in your NCERT book, figure 5.3. This is figure 5.3. This is figure 5.3, which will illustrate you about mechanism of heterogeneous catalysis. They have not shown the diffusion. I have shown you the diffusion first step. So total 5 steps are there in the mechanism. Is it clear, students? We shall now go for the next part. Okay, now let us study the differences between, important for the annual examination, differences between homogeneous and heterogeneous catalysis. Homogeneous and heterogeneous homogeneous and heterogeneous catalysis. Homogeneous and heterogeneous catalysis. Okay, students, draw two columns. Let us study in the form of differences. So draw two columns. One column you write homogeneous catalysis, and second column you write heterogeneous catalysis. Column number 1, let us write it as homogeneous. Homogeneous catalysis. This difference can be asked for 2 marks, students. Give any two differences between homogeneous and heterogeneous. Let me write here as heterogeneous, heterogeneous catalysis. Homogeneous and heterogeneous catalysis. Let us study as 2 points of differences. Okay, start noting down point one by one, students. Now tell me, homogeneous catalysis, whether there would be difference in the phase of the reactants, products and the catalyst? No, all of them would be in the same phase. So we call it as catalyst and reactants are in single phase. Catalyst and reactants are in single phase, Is it point clear, students? Now can you tell me what is the characteristic of a heterogeneous catalysis? When you write it as differences, it should be looking like a difference. Catalyst and reactants, catalyst and reactants are in different phases. I think this point is clear, students. Point number 2, generally you know that for homogeneous catalysis solid is not involved. Generally the reaction medium would be in the phase of either gases or in terms of liquids. Reactions generally occurs in the liquid phase. I'll write as L phase, the liquid phase. L stands for liquid, L phase, or gas phase, or for gas I'll write as G phase. G stands for what, students? Gas. Generally homogeneous catalysis reaction occurs in liquid phase or in the gas phase. Here generally reaction do not occur in liquid phase or the gas phase. Generally reaction does not occur in gas or liquid phase. Then it occurs in what phase? It does not occur in gas or liquid phase, but it occurs in let us write as on the surface of solid catalyst, Is this point clear, students? The second point of difference is clear to you now. Now, since the homogeneous catalysis is taking place in a single phase, the rate of the reaction do not change. Rate of the reaction does not depend on the surface area of the catalyst. I think this point is clear. The rate of the reaction, I'll write in short, reaction does not depend on surface area, does not depend on surface area. I'll write as SA, surface area of catalyst. catalyst. Is it clear, students? Then here you know that since it is happening on the surface of a solid catalyst, more the surface area is available, more would be the rate of the reaction. So therefore I can say that rate of the reaction, let me write as reaction, is directly proportional to the surface area of the catalyst. I think this point is clear, students. The surface area of the catalyst. Point of difference. The catalyst would dissolve, since it is all in the same phase, catalyst would dissolve and separating them at the end would be difficult. The catalyst dissolves into the gas phase or into the solution phase, that is of a reacting mixture. Here it do not dissolve, so separating would be easy. So I can say that catalyst dissolves into the gas phase, catalyst dissolves into gas phase or solution, Here what should I write as a point of difference? Catalyst do not dissolve, does not dissolve. Is it clear, students? Catalyst does not dissolve. Still few more points can be written. Homogeneous reactions generally occurs faster because we know that all of them are in the same phase, whereas since you have a solid involved in the reaction would be slower when compared to this homogeneous catalysis. Catalyst can be easily separated in heterogeneous catalysis, but here catalyst cannot be easily separated from the products of the reaction because they are all in the same phase. So these are some few important differences between homogeneous catalysis and heterogeneous catalysis. Now the points which I have not written here, I told it only, I'll write it in the beginning, students. I'll write it here. I've told you two important points. Let me write it here. The two important points are said to be: catalyst cannot be easily separated. Catalyst cannot be easily separated. Cannot be easily separated. Cannot be easily separated. Easily separated. Whereas in this case, catalyst can be easily separated as the catalyst is a solid. Catalyst can be easily separated, Generally, the next point what I said was, I'll write it in a different color. So these reactions are faster. So homogeneous catalyzed reactions are faster as compared to heterogeneous. So this will be slower. I think all these points are clear, students. This point of difference can be asked for 2 marks. So any 2 points of differences can be asked in the annual examination. Just look into all the important points of differences. Let me continue with the next part. So let me tell you what are the important points of differences that I told you. The important points of differences that I told you are: 1. Catalyst and the reactants are in the single phase. Heterogeneous, they are in different phases. Second point, reaction occurs in liquid phase or the gas phase. Reaction does not occur in the gas or the liquid phase but occurs on the surface of a solid catalyst. The rate of the reaction does not depend on the surface area of the catalyst as there is no solid substance. Here, the rate of the reaction is directly proportional to the surface area of the catalyst. Next point what we have studied was catalyst dissolves into the gas phase or into the aqueous solution or solution medium, catalyst does not dissolve. Since it is dissolving and here it is not dissolving, catalyst cannot be separated easily. Here catalyst can be easily separated. Since all of them are in the same phase, this homogeneous catalyzed reactions are faster when compared to the heterogeneous reactions. So therefore, heterogeneous reactions are said to be slower. Okay, let us go for the next point that we have studied, that we need to study, is that general characteristics of, so this can be asked for 2 marks, students. General characteristics general characteristics general characteristics of catalysts. Few important points, you can refer your study material, so I'll keep on explaining point by point. Point number 1, very important point, is that catalysts are always regenerated during the reaction. Catalysts, you know that it is not consumed. Catalyst is regenerated during a reaction. Catalyst is regenerated during a reaction. Let me give you a proof for this statement. It is not being consumed. Is the point clear, student? Now let me say that we have the oxidation of sulfur dioxide, 2SO2 plus O2, leading to the formation of 2SO3. Let me say that this oxidation can be catalyzed either by V2O5, it can be catalyzed by NO, or it can be catalyzed by NO2. For illustrating, let me say NO2 is being used as a catalyst. NO2 is being used as a catalyst. Is it clear, students? Now let me explain the mechanism of this reaction, how the reaction takes place. Mechanism. Let me explain you the mechanism of the reaction. Now, in step number 1, the reaction happens in 2 steps. Let me say step number 1, let me say that sulfur dioxide, 2SO2 gas, would combine with 2NO2 gas, so as to form 2SO3 gas plus 2NO. See, 2NO, what has been formed, this is called as an intermediate. In step number 2, 2NO gas is going to combine with O2 gas so as to form 2NO2 gas. See, the catalyst which was consumed in the first step has been regenerated. Now, if I want to get the overall equation, I have to add these two. Let me say that when I am going to add these 2 equations, let me call it as overall equation. Now we can clearly see that this NO and this NO gets cancelled. So now we can say that this 2NO2 and this 2NO2 would be cancelled. So therefore we can say that NO2 is not consumed during the reaction. Overall equation becomes 2SO2 plus O2, leading to the formation of 2SO3. Is this point clear, students? See, now we can say that NO2, which was used for the reaction, so where it was consumed, it has been regenerated. So therefore, ultimately this NO2 remains as such. It is not consumed during the reaction. So this is the proof for what? The first statement, the first general characteristic property of a catalyst. Catalyst is always regenerated during a chemical reaction. Note it down, students. Okay, students, I think you have noted down. Shall we give for the second property? First, what was the first property? Catalyst is regenerated during a reaction. It was the first characteristic property. Now let me teach you the second property. Assume that, let me say that the second property what I'm going to teach is that catalyst is not going to affect the equilibrium constant. So catalyst does not affect, catalyst does not affect, catalyst does not affect, catalyst does not affect equilibrium constant, does not affect equilibrium constant. You have studied this point even in your first PUC equilibrium chapter. Now for this instance, to explain this, I'll tell you that you have a reactant A which reversibly gets converted into B. Is it clear, students? Now say that for this reaction we have used a catalyst. Let us write a catalyst is being used for this reaction. Catalyst is being used for this reaction. The catalyst what we have used, which will increase the rate of forward reaction, the same catalyst will increase the rate of backward reaction also, but the increase in the rate of backward reaction and forward reaction would be at the same rate. Increase in the rate of forward as well as backward reaction would be done equally. So catalyst does not shift the equilibrium, but it helps to attain, it helps to attain equilibrium quickly. It helps to attain equilibrium quickly. It helps to attain equilibrium quickly. I think this point is clear, students. Catalyst does not affect the equilibrium constant as it is increasing the rate of forward and backward reaction to the same extent. And now we can say that then what is the use of a catalyst? It helps to attain the equilibrium quickly. So that is the second characteristic property of equilibrium, is the second important characteristic property of a catalyst. Third important point is that what quantity of the catalyst has to be used for the reaction. Should we use large quantity? Should we use in small quantity? So catalyst means it should be always in a small quantity. So the third important characteristic property of this is that an extremely small amount of catalyst causes considerable increase in the rate of the reaction, increase in the rate of the reaction. Is it clear, students? Increase in the rate of the reaction. Let me give an example. If I want to say that hydrogen peroxide has to be decomposed, 2H2O2, in the presence of very small amount of platinum as catalyst, decomposes to give you 2H2O plus O2. Now you need to remember, students, what would be the concentration of platinum that we have to use for the reaction. The presence of very small amount, let me say that 10 to the power of minus 8 molar, a very small concentration in the order of 10 to the power minus 8 molar of colloidal platinum shows a significant increase in the rate of decomposition. Another important statement I can make, so if you are a biology student, you can understand better. One molecule of enzyme catalyzes under certain condition decomposes nearly 5 million molecules of hydrogen peroxide in 1 minute. So you have to remember one molecule of enzyme catalyzes the decomposition of 5 million molecules of hydrogen peroxide in 1 minute. Now you can understand. So what is the efficiency of a catalyst? It is a highly efficient catalyst. One molecule is going to catalyze 5 million molecules. One molecule of this enzyme acts as a catalyst, decomposing 5 million molecules of hydrogen peroxide in 1 minute. Is it clear, students? So this is said to be the third important characteristic property. An extremely small amount of catalyst would be sufficient to catalyze a reaction. So therefore we don't have to take in large quantities. If we take it in very small quantities, that would be sufficient. I have given you the example. A colloidal solution of platinum in the concentration of 10 to the power of minus 8 molar would catalyze the decomposition of hydrogen peroxide into water and oxygen. One molecule of enzyme catalyzes 5 million molecules of hydrogen peroxide decomposition in 1 minute, so that you can understand what is the efficiency of a catalyst. Is it clear, students? Next. Let me write the fourth important property, that is a catalyst will decrease, a catalyst decreases the activation energy of the reaction, decreases the activation energy of the reaction. If a catalyst is decreasing the activation energy of the reaction by proceeding through an alternate path, definitely you should understand that what should happen to the rate of the reaction. Rate of the reaction increases. For instance, let me say that if hydrogen peroxide H2O2 is decomposing so as to give you H2O plus half O2 in the absence of a catalyst, let me say the activation energy for this reaction is 76 kilojoules per mole. What is activation energy, students? Without the catalyst, it is 76 kilojoules per mole. Say that I am doing the same reaction, decomposition of hydrogen peroxide H2O2 so as to form H2O plus half O2. In the presence of catalyst, so let me say that the catalyst that is being used for this reaction is I minus. Alkaline iodide is used as a catalyst. Now the activation energy of this reaction is decreased, so it is 57 kilojoules per mole. Definitely you can understand, in the presence of I minus as a catalyst, activation energy of the reaction has decreased from 76 to 57 kilojoules per mole. So what should happen to the rate of the reaction? So rate of decomposition increases. In the presence of iodide ion as a catalyst. Rate of decomposition increases in the presence of I minus as the catalyst. I think this point is also clear, students. Now the next important characteristic feature of the catalyst. So that is a fifth property that we are going to study. Let me say that point number 5 that we need to study is that in your chemical kinetics chapter, you have studied what is the effect of a catalyst on the rate of a chemical reaction. Is it, students? Let me draw the graph of the reaction so that you can understand easily. Let me say that we are plotting the graph of reaction in progress. Or you can also call it as reaction coordinate, or you can also call it as reaction coordinate, or I can also write it as reaction coordinate. Is it clear, students? On to the other side, I have to write here as potential energy. This should be potential energy. As we move up, potential energy increases. As we move from left to right, the reaction is in progress. So we can call it as time also in other way. Now every reactant would have certain amount of energy. Let me say that it is having certain amount of energy. It has to collide so as to form the products, and it has to form an activated complex, and it has to decompose so as to give the product. Now let me say that this is said to be the average energy of the reactants. Let me write it here. This is said to be the average energy of the reactant. Let me call it as average energy of the reactant, ER. Let me say this is said to be the average energy of the product, so which you have studied in the chemical kinetics chapter. Let me call it as average energy of the product. In the presence of a catalyst, the reaction totally proceeds in an alternate path. Let me call this as reactant. Let me call this as the product. So it would move in an alternate path where the activation energy of the reaction is less. Where the activation energy of the reaction is said to be less. Now I can say that this is called as EA. This is called as EA. Let me write it here, students. So this is called as EA. This is called as activation energy. This is called as EA. In the absence of catalyst, in the absence of catalyst, let me say this is said to be the activation energy in the presence of catalyst. Let me say this is said to be the activation energy. Let me say that this is said to be the activation energy. Let me write it here, EA dash, activation energy in the presence of catalyst. In the presence of catalyst. In the presence of catalyst. Is it clear, students? Now you can see the energy difference between the reactant and the product. So let me say, so this is called as delta H of the reaction. Delta H of the reaction is equal to energy of the product minus energy of the reactant. Correct? Now you can see whether the reaction is happening in the presence of catalyst or in the absence of catalyst, whether this delta H of the reaction changes. No. So whether it is catalyzed or the uncatalyzed reaction, it is not going to change the enthalpy of the reaction. So therefore that is the one that we need to highlight here. A catalyst does not affect delta H of the reaction. It does not affect the delta H of the reaction. It does not affect the delta H of the reaction. Whether it is a catalyzed reaction or an uncatalyzed reaction, it would remain the same. It is not changing. Is it clear, students? You can note it down. Okay, shall I go for the next point, students? Next important property is that, next important general characteristic property is that a catalyst does not initiate a reaction. A catalyst does not initiate a reaction. Does not initiate a reaction. It only catalyzes the reaction which is happening. It only enhances, it only enhances the rate of a reaction. Rate of a reaction. It is not initiating a reaction, but it will make the reaction which are happening at a slower rate to happen at a faster rate. Anyhow, you know that in chemistry always there will be some exceptional cases. However, in certain cases catalyst is found to initiate the reaction. For example, exception for this statement what we have written, a catalyst does not initiate a reaction, it only enhances the rate of a reaction. If you take hydrogen and oxygen, both gases are present in the atmosphere, it remains unchanged. It remains unchanged. It remains unchanged at 25 degrees Celsius for years together. You keep it for any number of years, it is not going to change. But in the presence of platinum, in the presence of platinum, this H2 and O2 starts reacting immediately, and the reaction becomes so high that the mixture explodes. H2 and O2 mixture explodes. Is this point clear, student? In the presence of platinum, this H2 and O2 mixture would react so fast immediately so that the mixture explodes. So this is an exception for this statement. A catalyst does not initiate a reaction, it only enhances the rate of a reaction. Is this point clear, students? So these are said to be certain important general characteristics of the catalyst. So let me tell you what are the important points that we have started studying about the general characteristic properties. Point number 1 is catalyst is always regenerated, that we have already studied. You can go back for the things what you have written, students. Do you see that? First point that we have studied is catalyst is always regenerated. When sulfur dioxide is oxidized into SO3 in the presence of NO2 gas as catalyst, we have seen that NO2 is regenerated during the reaction. Second point that we have studied was that a catalyst do not affect the equilibrium constant. It helps only to attain the equilibrium quickly. It increases the rate of forward and backward reaction to the same extent. Third point that we have studied about the property was that an extremely small amount of catalyst causes considerable increase in the rate of the reaction. In the example I gave you, the decomposition of hydrogen peroxide in the presence of colloidal platinum in the order of 10 to the power of -8 molar would be sufficient to decompose hydrogen peroxide. Another example for highly efficiency of the catalyst, I have given the example of one molecule of an enzyme can catalyze the decomposition of hydrogen peroxide in 1 minute, is that 5 million molecules of hydrogen peroxide is decomposed. Fourth point that we have discussed is that a catalyst is going to decrease the activation energy of the reaction, thereby increasing the rate of a chemical reaction. I gave you the example of, in the absence of hydrogen peroxide, activation energy for hydrogen peroxide decomposition is 76 kilojoules per mole, and in the presence of catalyst, the activation energy will be reduced to 57 kilojoules per mole, thereby rate of the reaction would be more. How does it decreases the activation energy? By totally proceeding in an alternate path. And what was the catalyst that was used for the decomposition of hydrogen peroxide, students? Iodide ion. Point number 5 that we have studied was catalyst does not affect the energies of the reaction, that is enthalpies of the reaction. So energy would remain same whether it is a catalyzed reaction or an uncatalyzed reaction. It only increases the rate of reaction and helps to attain the equilibrium quickly. Point number 6 we have studied, a catalyst does not initiate a reaction, it only enhances the rate of the reaction, and the exception that we have studied was H2 and O2 remains unchanged. But in the presence of small amount of platinum for the mixture of H2 and O2, it reacts starting immediately, and the reaction becomes so high and rate of the reaction becomes so high and the mixture starts exploding. Sometimes, students, in order to increase the efficiency of a catalyst, so we need to add certain substances. In order to decrease the activity of a catalyst, we will be adding certain substances. So we need to study what are those substances called as. What did I tell? Sometimes in order to enhance the activity or efficiency of a catalyst, we need to add certain substances. Sometimes to decrease the activity of a catalyst, so we need to add certain substances. What is that called as? So we should know what is that, the definitions of that, and 1 or 2 examples let me give you. So let me say we are going to study the concept of promoters and poisons. Promoters and poisons. We need to know these two things. What are promoters and what are said to be poisons? Is it clear, students? Now, let me say that during the manufacture of ammonia by Haber's process earlier, N2 gas and H2 gas was mixed so as to give you NH3 gas. Let me write it as 2NH3 gas. The yield of the reaction is very low and the reaction is taking place very slowly. So therefore, we have to use catalyst. In olden days, the catalyst that was used was said to be iron. In order to increase the efficiency of iron, we were adding certain substance that is called as molybdenum. Now we said that in this case, iron is said to be a catalyst. Iron is said to be catalyst. Nowadays, the iron catalyst is being replaced by iron oxides, a non-stoichiometric oxide, and MO was used in the earlier days, and just to enhance the activity, just to increase the activity, just to increase the efficiency of a catalyst, and we call this as a promoter. We call this as a promoter. Now tell me, students, what are promoters? Promoters are substances that enhances the activity of a catalyst. This can be asked. Now give me an example for promoter, students. During the manufacture of ammonia by Haber's process, iron is used as a catalyst and molybdenum is used as a promoter. Is it clear, students? Now, there are certain substances which would decrease the activity of a catalyst. For example, you have 2SO2. It is subjected to oxidation so as to form sulfur trioxide, 2SO3. Now, presence of small amount of platinum would catalyze the reaction. This platinum is said to be the catalyst. Let me say this platinum acts as a catalyst. Platinum would act as a catalyst. It acts as a catalyst. Now, if I add small amount of arsenic, this arsenic is going to combine with platinum and it is going to become PTAS2, platinum arsenide. It leads to the formation of PTAS2. Once if it forms PTAS2, the catalytic property of platinum is lost because of the combination of platinum with arsenic. Its surface area of free valencies so as to form the bonds with the sulfur dioxide and O2. So its catalytic property would be lost because of the formation of this compound, and hence the activity of the catalyst is decreased, and we call certain substances which are used to decrease the activity of the catalyst as poisons. What do we call it as? Poisons. These are called as poisons. Now, what is the definition of a poison? Poisons are the substances that decreases the activity of a catalyst, 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 that decreases the activity of a catalyst. Is it clear, students? Activity of a catalyst. Example that I have given is that for the oxidation of sulfur dioxide to sulfur trioxide, Platinum acts as a catalyst, and addition of small amount of arsenic will make platinum to combine with arsenic so as to form PtAs2, so which will act as a poison, which will decrease the activity of a catalyst, and what do we call such things as poisons. Is it point clear, students? Shall we go for the next point? Shall we study the next concept, students? So there is a small word called as activity of a catalyst. There is a simple word called as activity of a catalyst. So what do you mean by the activity of a catalyst? The efficiency of a catalyst. The activity of a catalyst depends upon what? It depends on the strength of chemisorption, strength of chemisorption to a larger extent. It depends on the strength of chemisorption. What is that chemisorption means? The reactant molecules has to form bonds with a catalyst. That bond form, the reactants must be absorbed on the surface of a catalyst, reasonably strong on the surface of a catalyst, reasonably strong. If it is very strongly held, then those would be immobilized and the other reactants are left with no space on the catalyst surface for adsorption. If it is very loosely held, then there would be no scope for the interaction of the reactants. So therefore, it has to be adsorbed reasonably strong, not very strong, not very loose, it should be reasonably strong, so that once if the reaction is over, it can be disrobed and it gives the scope for the next reaction. And the third important point is that it has been found that for hydrogenation reaction, you have studied hydrogenation is nothing but addition of hydrogen in the presence of platinum or palladium or nickel as catalyst. You have studied these reactions in your organic chemistry. It is found that for hydrogenation reaction, so there would be increase in the catalytic activity from group number 5 to group number 11 in the periodic table, with maximum activity being shown by group number 7 to 9, maximum activity for the catalytic property of hydrogenation during hydrogenation is shown by group number 7 to 9 elements of the periodic table. So this is somewhat we call it as activity of a catalyst. This is also said to be one of the property of a catalyst. Is it clear, students? Now, next important point is that we have to study selectivity of a catalyst, whether any catalyst would catalyze any reactions. No, it will not catalyze anything, cannot catalyze any reaction. Any catalyst cannot catalyze any reaction. It catalyzes only certain reactions. But you have the same reactants in the presence of different catalysts. Will it give different products? Definitely. What do we call that as? We call it as selectivity of a catalyst. So under the concept of selectivity, let me write you certain important reactions which have already studied in your NCERT book. So in different chapters, either in first year or in the second year. I think students you can remember carbon monoxide is going to react with 3 moles of H2 in the presence of nickel as catalyst so as to form CH4 plus H2O. You have studied this in hydrogen chapter of first year. We know that a mixture of carbon monoxide and hydrogen is called as a syngas, or it is also called as water gas. Why it is called as a syngas? Because it is used in the preparation of many organic compounds. So you can say that in the presence of nickel as catalyst, it forms methane and water, which you have studied in first PUC hydrogen chapter. And second reaction, what I'm writing now, you have studied in your second PUC alcohols, phenols and ethers chapter. Carbon monoxide is mixed with hydrogen gas in the presence of copper, in the presence of ZnOCr2O3 catalyst, in the presence of ZnOCr2O3 as catalyst, so as to form wood spirit, that is methanol, CH3OH. In the last part of the alcohol phenols ether, some industrially important compounds. So you have studied under that industrially important alcohols like methanol and ethanol preparation. So ethanol preparation was from the fermentation of cane sugar, and you have studied about the preparation of methanol from the mixture of carbon monoxide and H2 in the presence of copper, zinc oxide and Cr2O3 catalyst. And the third reaction, this you have studied in your first PUC chapter, so that is in hydrogen chapter, carbon monoxide and H2 gas. So in the presence of copper as catalyst, the presence of copper as catalyst is leading to the formation of HCHO. Formaldehyde is being formed. Now you can see the selectivity of a catalyst. The selectivity of the catalyst is the ability to direct a reaction to a particular product. So this is what we say, particular product, in the sense nickel will direct so as to give methane, copper, zinc oxide, Cr2O3 will direct the mixture of carbon monoxide and H2 gas so as to give methanol, copper will direct COH2 gas so as to form formaldehyde. So students, what is selectivity of a catalyst? The selectivity of a catalyst is the ability, the selectivity of a catalyst is the ability to direct, ability to direct is the ability of what? Is the ability of a catalyst to direct, is the ability of a catalyst, is the ability of a catalyst to direct a reaction, to direct a reaction, direct a reaction, to direct a reaction to yield a particular product, to yield a particular product, yield a particular product. Is it clear, students? Selectivity is the ability of a catalyst to direct a reaction to yield a particular product. Is it clear, students? So I have given 3 examples now: carbon monoxide, H2 gas, carbon monoxide, H2 gas, carbon monoxide, H2 gas. In the presence of different catalysts will give you different products, and the ability of this catalyst to direct so as to give different products in the reaction is called as selectivity of a catalyst. I think this point is clear, students. Let me go for the next point, that is another kind of catalysis. We call it as shape selective catalysis. Another kind of reaction, we call it as catalysis, that is called as shape selective catalysis. Shape selective, shape selective catalysis, shape selective catalysis. There are certain catalysts which depends on the pore structure of a catalyst and size of the reactant and the product molecule. So what is shape selective catalysis, students? The catalytic reaction that depends on the catalytic reaction, the catalytic reaction that depends on pore structure, that depends on pore structure, that depends on pore structure of catalyst, that depends on the pore structure of catalyst, and size of reactant and product, reactant and product, reactant and product. Reactant and product molecule is called as shape selective catalysis. Very important, students. Certain definitions has to be by hearted in this chapter. So shape selective catalysis. Now, an example for the shape selective catalysis is that zeolites. Example is that zeolites. Students, you have studied about zeolites in detail in your first PUC, P block elements. At the end of P block, group number 14. Tell me, students, what are zeolites? Zeolites are hydrated aluminosilicates, which we have used this for the removal of permanent hardness of water. So zeolite method we have studied. Is it clear, students? Now let me show you the diagram of this. Let me show it here, students. See, students, now you can see can you see, students? This is called as honeycomb structure. Zeolites would be having honeycomb structure. Zeolites, I think you can see it has a honeycomb like structure. This is one of the structure, and you can see all these things. This looks like a honeycomb. So we call it has honeycomb like structure. Zeolites are good shape selective catalysis because of their honeycomb like structure. They are microporous aluminosilicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminum atoms, giving ALOSI framework. So this statement is given in your NCERT, students. You can see it was asked in the annual examination March 2020. So the question was, why zeolites are good shape selective catalysis? It was asked in the examination. See the diagram, students. I think you can see this is the diagram of honeycomb structure. You can see it very clearly. This is the diagram of honeycomb structure of zeolites, and the other two-dimensional structures is shown here. I think you can see in this. You can see another structure. You can see this structure also, where you can see the honeycomb structure. See here you have microporous structures, and you can also see here, this is here also you can see the microporous structure that is called as honeycomb structure. Due to the presence of honeycomb structure of zeolites, it shows good shape selective catalysis property. Is it clear, students? Shall we go for the next concept? So I told you that this was asked in your first PUC annual examination, second PUC annual examination, March 2020 examination. Why? Note down the question, students. Why zeolites are good shape selective catalysts? Why zeolites are good shape selective catalyst? This was asked in 2020 annual examination. Why zeolites are good shape selective catalyst. Shape selective catalyst. This was asked in March 2020 annual examination. March 2020 annual examination. Very important question. So students, what is the answer? Zeolites are good shape selective catalysts because of their honeycomb like structure. Honeycomb like structure. Is it clear, students? So this was asked in the annual examination of this year. So you need to remember why zeolites are good shape selective catalyst, because of their honeycomb like structure. The alternate answer that can be given are They have microporous aluminosilicates with three-dimensional network of silicates. So that also can be given as the statement. Now, one of the catalysts that you have studied in your first POCP block, I'll give it as an example. Example is that ZSM5. ZSM5 is a good shape selective catalyst, that is zeolite, used in the petrochemical industry, used in the petrochemical industry, used in the petrochemical industry, used in the petrochemical industry for cracking, for, I can say, for conversion of alcohols to gasoline, alcohols to gasoline directly, for the conversion of alcohol into gasoline directly. Are these points clear, students? Just have a note on it, see it once. Shall we go for the next part, students? I'll erase it. Okay, students. Next one is that we have to study about enzyme catalysis. We have to study about enzyme catalysis. Enzyme catalysis. Enzyme catalysis. First of all, we should know what is an enzyme. A simple definition for an enzyme. Biology students, can you tell me what can you think about what is an enzyme? And simply, if I should say, enzymes are biological catalyst. These are biological catalyst. Biological catalyst. This is a very simple statement to understand what is an enzyme. Enzyme is a biological catalyst, or I can call it as a biochemical catalyst. The proper definition for an enzyme goes like this: complex nitrogenous organic compounds which are produced by living plants and animals are called as enzymes. So what are enzymes? Enzymes are complex, enzymes are complex nitrogenous organic compounds, nitrogenous are complex nitrogenous organic compounds, nitrogenous organic compounds, nitrogenous organic compounds which are produced by living plants and animals, by living plants and animals, living plants and animals. Is it clear, students? So I can say they are actually proteins. They are nothing but proteins. They are nothing but proteins of high molecular mass. They are proteins of what? High molecular mass. They are proteins of high molecular mass. They are proteins of high molecular mass. And it forms a colloidal solution with water, and it forms a colloidal solution, and it forms a colloidal solution. It forms a colloidal solution, it forms a colloidal solution in water. It forms a colloidal solution in water. I think these points are clear, students. So in short, I say thus enzymes are termed as biochemical catalyst, and the phenomenon where it is being used is called as biochemical catalysis. So we need to study something on this. So what is that, students? Studying about enzyme catalysis. I'll give you some examples for enzyme catalysis. I'll give you some important examples for enzyme catalysis. So first note it down, students. Okay, students, shall we go for the next part? Examples. I'll give you the example for enzyme catalysis. I think the point is clear, students. Write examples of enzyme catalysis. Examples of enzyme catalysis. Examples of enzyme catalysis. First example is the inversion of cane sugar. Inversion of cane sugar. Inversion of cane sugar. Inversion of cane sugar. First, I'll write the equation. Tell me what is cane sugar? Sucrose, C12 H22O11 is hydrolyzed. I'm adding water, H2O. In the presence of the enzyme, we call it as invertase enzyme. What is the name of that enzyme, students? Invertase enzyme. In the presence of invertase as an enzyme, it gets converted into glucose and fructose. Let me write it as glucose. Let me write the formula, students. C6H12O6, this is glucose, and another molecule, let me write as C6H12O6. So first molecule, if I write it as glucose, the second molecule is called as fructose, and this is cane sugar. This is cane sugar. Inversion of cane sugar in the presence of the enzyme invertase takes place. Biology students might have studied this. Second example for this enzyme catalysis is the conversion of glucose, C6H12O6, glucose or fructose, I can say glucose or fructose, I can also say or fructose, glucose or fructose. In the presence of enzyme zymase, 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 where did you study this, students? In the manufacture of ethyl alcohol. In the manufacture of ethyl alcohol, I think you have studied this. So invertase would convert sucrose into glucose and fructose, and glucose or fructose can be converted into ethyl alcohol. Let me write it as ethyl alcohol, C2H5OH, and water, and carbon dioxide. So 2C2H5OH and 2CO2. We have studied both of these equations in the chapter of alcohol, phenols and ethers, and we call this as ethyl alcohol. This is called as ethyl alcohol. The other one is carbon dioxide. So the third example that I can give you for this is that the third example that I can give is the decomposition of urea so as to form ammonia and carbon dioxide in the presence of urease enzyme. So NH2CO NH2, this is called as urea. This is called as urea. If I add water, in the presence of urease enzyme, it gets converted into ammonia and carbon dioxide. It gets converted into ammonia and carbon dioxide. Another example that I can give for this, so I think students, you have noted down all these 3 examples. So I'll give you 2 more examples. Let me give you the example of example number 4. So milk can be converted into curd. Milk can be converted into curd in the presence of lactobacilli. In the presence of lactobacilli. In the presence of lactobacilli. I think all these points are clear, students. I have given you 4 important examples for enzyme catalyst. So n number of examples you have studied in your biology class, and if you remember this many things, that would be sufficient. Okay, now let's go for the properties of enzymes. Let's go for studying the properties of enzymes. Let's start studying about the properties of enzymes. Properties of enzymes. Properties of enzymes. First property of enzyme is that it is highly efficient. First property of enzyme is that it is highly efficient. Highly efficient catalyst. It is highly efficient catalyst. It is a highly efficient catalyst. So you should know that it increases enzyme catalyst. Enzyme catalyzes the reaction. Enzyme catalyzes the reaction. Catalyzes the reaction. Catalyzes the reaction by 10 to the power 8 to 10 to the power 20 times. You can understand what, by how many times the rate is increased. 10 to the power 8 to 10 to the power of 20 times. So just a statement, if there were no enzymes in our digestive system, it would have taken 50 years to digest a single meal. So now you can understand what is the efficiency of a catalyst, enzyme catalyst. If there were no enzymes in our digestive system, if we take one time meal, it would take 50 years to digest that. So I think you can understand now, per day we'll have 5 meals, sometimes 6 meals, so and many more times. So all the food that we eat is digested due to the presence of certain enzymes which is there in our digestive system. So you can think about what is the efficiency. It is a very highly efficient catalyst. Second point, specificity. 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 Each enzyme catalyzes only certain chemical reactions. Each enzyme, I can say that each enzyme catalyzes only one chemical reaction. One chemical reaction. One chemical reaction. Example, I can say urease catalyzes the enzyme urease. This is an enzyme. This will catalyze only the hydrolysis of urea. It catalyzes only the hydrolysis of urea. It catalyzes only the hydrolysis of urea. It catalyzes only the hydrolysis of urea and not N-methyl urea and not N-methyl urea and not N-methyl urea. So students, you know what is the structure of urea? NH2, C double bond O, NH2. What is the structure of N-methyl urea? So I have to write here CH3, NH, C double bond O, NH2. See, this is the structure of N-methylurea. You can see the functional group almost remains same. You have CO group as the functional group. Here also have CO group. The only difference is that one hydrogen, here one hydrogen is replaced by CH3 group. Even though it is structurally almost the same, but still it is not catalyzing that reaction. I think this point is clear, students. Point number three that you have to know is that presence of very small quantity of catalyst would be sufficient. Presence of a small quantity of the catalyst is sufficient. Point number three, small quantity of the catalyst is sufficient. Why small quantity is sufficient? Why small quantity is sufficient? Because it is regenerated. It is regenerated during the reaction. It is regenerated. Point number four, there is something called as a particular temperature where the activity of the catalyst is maximum. So we call it as optimum temperature and optimum pH. Optimum temperature and optimum pH. So you have to remember this, students. Enzyme catalyzed reactions have maximum rate at physiological, that is human body, at the physiological conditions, let me say in the human body, at a temperature of 37 degrees Celsius, normal human body temperature, and at a pH of 5 to 7. It's slightly acidic. So optimum temperature for the maximum efficiency of the catalyst, enzyme catalyst, is 37 degrees Celsius and the pH would be 5 to 7. I think this point is clear, students. And there would be certain things which increases the activity, just like we had studied about promoters, and we have studied something called as poisons, which decreases the efficiency of a catalyst or activity of a catalyst, increasing the activity in the presence of activators and coenzymes. So efficiency, or I can call it as increasing the activity, increasing the activity of a catalyst, increasing the activity of a catalyst, that is enzyme catalyst, in the presence of activators and coenzymes like Na plus or Mn2 plus, or maybe cobalt 2 plus, or maybe Cu2 plus, etc. The presence of these kind of things, we call it as coenzymes or activators, would enhance the efficiency or increase the activity of an enzyme catalyst. So there can be certain things just to inhibit, as we had studied about poisons there, here we are studying, so we call it as inhibitors and poisons. Influence of inhibitors and poisons. So we can give the example of drugs. Drugs would bind into the active surface of the catalyst and it acts as an enzyme inhibitor. It acts as an enzyme inhibitor. I think all the properties of enzymes are very clear to you, students. What are the important properties of the enzyme catalyst that we have studied? So enzyme catalysts are highly efficient. I have given you an example. So enzyme catalyst increases the rate of a chemical reaction by 10 to the power 8 to 10 to the power 20 times. I think this point is clear, students. So specificity, each enzyme catalyzes only certain chemical reaction, that is one chemical reaction. Example, enzyme urease catalyzes only the hydrolysis of urea and not N-methylurea, which is very similar in its structure. I have written the structure. And presence of small quantity of catalyst is sufficient as the catalyst is regenerated during the reaction. optimum temperature and pH. I told you what is optimum temperature and what is said to be optimum pH. Tell me, students, what is optimum temperature? The rate of an enzyme reaction becomes maximum at a definite temperature called as optimum temperature. The optimum temperature range for an enzyme catalyst is between 298 to 310 Kelvin. So I wrote only one particular temperature. If I want to write the range of temperature, students, so it should be from 298 Kelvin to 310 Kelvin. This is from 25 degrees Celsius to 25 degrees Celsius to 25 degrees Celsius to 30 degrees Celsius, 25 degrees Celsius to 30 degrees Celsius. I think you can understand this, students. 37 degree corresponds to, yes, correct, 298 Kelvin to 310 Kelvin. I think these points are clear. 25 degrees Celsius to 37, sorry, this is 37 degrees Celsius, 37 degrees Celsius. Tell me, what is the definition of optimum pH? The rate of enzyme catalyzed reaction is maximum at a particular pH called optimum pH, which is in between 5 to 7. That also I have written. So then in the presence of certain things, like we call it as activity can be increased in the presence of activators, or we can call it as coenzymes. Then influence of inhibitors and poisons. So like ordinary catalyst, enzymes are also inhibited or poisoned by in the presence of certain substances. So I have given you drugs would bind into the active surface of the enzyme and inhibits the catalyzed reaction, enzyme catalyzed reaction. I think this point is clear, student. Next, biology students have studied about the mechanism of enzyme catalyst. Now let us see it in chemistry. Mechanism of mechanism of enzyme catalysis. Mechanism of enzyme catalysis. Mechanism of enzyme catalysis. Those who studied in biology, so you may know about it. Students, let me simply keep a diagram for you to understand. This is your NCERT diagram. Just simply look into the diagram, students, so that you can understand something when I explain. Students, see here. Let me say that this is said to be an enzyme catalyst. This part what we have taken is an enzyme catalyst. And let me say that this has a definite shape. Catalyst has a definite shape. And you can see that there will be a substrate, that is a reactant, which will be having a definite shape. So if the shape of this is matching with the shape of an enzyme, then this, if I call it as a key and a lock, this key can fit into this particular lock. So we can call this as a lock and key model. Once if the enzyme is going to bind to the substrate, once if this enzyme binds to the substrate, then it forms an intermediate. We call it as enzyme substrate complex. So any reactant cannot go and combine with this enzyme. If the shape, we call it as an active site, is matching its shape with that of the enzyme, then only it can form an enzyme substrate complex. Once if it forms an enzyme substrate complex, then it would decompose so as to form, so as to regenerate the enzyme, and this would be broken so as to give you the products. I think this point is clear, students. So what do we call this as? Mechanism of enzyme catalysis. So basically we call it as a lock and key model. So now you have to remember that there are a number of cavities present on the surface of colloidal particles of the enzyme. These cavities are characteristic shapes and it possesses active groups such as NH2, COOH, SH or OH. These are actually the active centers on the surface of the enzyme. We call it as active centers on the surface of the enzyme particles. These molecules of the reactants, that is substrate, which have complementary shape, we call this as a complementary shape, fit into the cavities like a key fits into a lock. On account of the presence of active group, an activated complex is formed which then decomposes to yield the products. It is a two-step mechanism. So I told you that E is said to be enzyme, S is said to be a substrate. Substrate is nothing but the reactant. So it is leading to the formation of enzyme substrate complex. This enzyme substrate complex decomposes to give you enzyme plus product. So enzyme is regenerated during a chemical reaction. Is that point clear, students? Next, at the end of this chapter, to summarize, so let me give you some examples of the catalyst which is used in the industries. So let me not write it again, students. So simply I'll write the heading catalysis. Catalysis in industry. Catalysis in industry. Catalysis in industry. Now, some of the important technical catalyst processes, catalytic processes are used in the industries. Let me show you that directly in the NCERT book. So let me read it out because you are studying these things in different chapters, students. So you can also note it down. You can also read it in your NCERT book. So you can see this. The first one is that in Haber's process, that is in the manufacture of ammonia, finely divided iron, molybdenum as a promoter. So conditions is 200 bar pressure and 723 to 773 Kelvin temperature. Nowadays, a mixture of iron oxide and potassium oxide and alumina is used. So I told you earlier also, so this is the old method, finely divided iron along with the molybdenum as a promoter was used. Nowadays, iron oxide along with potassium oxide as well as aluminum oxide is being used. You are going to study this in P block group number 15 once again. Second one, Ostwald's process. So I'm not going to say the details of this equation. You're going to study the details of this equation in the chapter P block, that is chapter number 7. So in group number 15, Ostwald's method for the manufacture of ammonia. First step is the aerial oxidation of ammonia so as to form nitric oxide. Second step is the oxidation of nitric oxide to nitrogen dioxide. And third step is said to be conversion of nitrogen dioxide into nitric acid. I think these points are clear, students. So in Ostwald's process, in the first step, so we need to use platinized asbestos. So temperature is 573 Kelvin. Pressure is not mentioned here. It is 9 bar pressure. And in contact process, for the oxidation of sulfur dioxide into sulfur trioxide, so we are using V2O5 or we are using platinized asbestos. So temperature is 673 to 723 Kelvin. So this will be taught in the chapter of P block. So group number 15. So these are certain important catalysts which are used in the industries. Is it clear, students? So you can note it down or you can refer your NCERT book. Is it clear? Just note it, students. Okay students, let us go for the next part. So we have finished the second part of surface chemistry. Now we are at the end of surface chemistry. So that is, we have to study something about colloids. We have to start studying something about colloids. For studying about colloids, students, we'll start with certain discussions so that you can understand the topic very easily. What are colloids? So we need to know the three types of solution. So one is true solution, one is colloidal solution, and we have three types. Let us see what are the three types now. So let me say that I have taken a beaker where I have some amount of water. I'll add some amount of salt. I'll add salt. Salt in the sense I'm telling NaCl. Salt is added. Then stir it. After stirring, can you see the particles? Once if you stirred, it becomes NaCl solution. Now can you distinguish between salt and water? Can you distinguish between salt and water? Can you distinguish between salt and water? Is it possible? Can you see? Once if you add NaCl into water, stir it. Once if you stir it, can you see the difference between Na, salt and water? Can you see it? So what is the answer? No, you cannot see the difference. You cannot see the difference. You cannot make out the salt and water separately. We call such kind of solutions as homogeneous solutions. What do we call it as? We call it as homogeneous solutions. What do we call it as, students? Homogeneous solutions. What do we call it as, students? Homogeneous solutions. Now let me tell that here the particle size is ranging between 0.1 to 1 nanometer. This is the size of particles in the homogeneous solution. You need to remember, students, what is the particle size in homogeneous solutions. Now let me say, students, let me say that I'm taking a beaker here. We have some amount of water. We have, let me also say here, water was present. Here some amount of water is taken. Some amount of water is being taken. For that I'm going to pour sand. Sand is poured into it. I'm going to pour sand. Sand is added, then stir it. I'm going to add sand and then I'm going to stir it. Once if you stir this, students, you can see the particles of sand. You stir it, you can see the particles of sand, or you cannot see the particles of sand. Just like in the case of when NaCl is added to water, you stir it. Can you see the salt particles? No. What do we call such solutions as? Homogeneous solution. When you stir sand, so when you stir the sand in water, so can you make out the sand and water? Can you make out the sand and water? Just think on it, students. Definitely you can say that you can make out salt. You can make out sand and water. You can see it as a different particle. Sand and water can be distinguished. It can be distinguished. So we call this as heterogeneous solution. What do we call it as? Heterogeneous. We call it as heterogeneous solution. We call it as heterogeneous. We call it as heterogeneous. What do we call it as, students? Heterogeneous. We call it as heterogeneous. We call it as heterogeneous. So now we call these kind of things. See, what is this? Homogeneous. We cannot make it out. So we call it as homogeneous. So these are actually called as, I can make a word called as true solutions. I can write this one as true solution. We call it as true solution. And now this is called as actually suspensions. This is called as suspensions. Is it clear, students? Now you should know that here the particle size would be greater than, particle size is greater than 10 to the power of 3 nanometers. Particle size, this is nothing but called as particle size. Particle size in suspensions would be greater than 10 to the power of 3 nanometers. Now let me say that I'm taking another beaker. I'm taking another beaker. In this beaker I have water. Let me say that I have water. I have taken water. For that I'm adding some amount of starch. Let me say it is little bit hot water. I'm adding starch, then I'm stirring it. When you stir it, when you stir that, so now can you see the particles? So you cannot see the particle, but it looks like somewhat milky water. So we call this thing as actually heterogeneous itself. This is called as heterogeneous. This is called as heterogeneous. But the particle size would range in 1 nanometer to 10 to the power of 3 nanometer. Particle size is in between 1 nanometer to 10 to the power of 3 nanometer. So this is a starch solution in water. So you cannot make out, or you may make out, it looks like a milky solution, but this would settle, this would not settle. So we call this kind of solutions as the last part of our chapter, that is colloids. We call this as colloids. Is this clear, students? So you need to remember all these things. In the last part, so we have studied now that when you stir a certain substances in water, either we may see it or we may not see it. So either we can make it out or we cannot make it out. So either it may settle or it may not settle. So now if we say that when salt is dissolved in water, we cannot see the salt particles even under powerful microscope. So then the particle size would be in the range of 0.1 nanometer to 1 nanometer. We call such things as homogeneous, and it is called as a true solution. When you dissolve starch in hot water or maybe water, so when you stir it, so it looks like milky, and the particle size would be in the range of 1 nanometer to 10 to the power 3 nanometers, and you may see the particles under powerful microscope or you may not see it also, and we call this kind of things as heterogeneous, and we call it as colloids. And if we stir sand in water, so if you stir it, you can make out clearly what is water and sand, and it would settle after some time, and here the size of the particle would be greater than 10 to the power 3 nanometers, and we call these kind of things as heterogeneous mixtures, or we can call it as suspensions. Is it clear, students? Now, as you have studied in the first part, adsorption, two important terms. What are the two important terms, students? One is said to be adsorbent, another one is said to be adsorbate. One is said to be adsorbent, another one is said to be adsorbate. Similarly, here in the case of colloids, so you need to know two important things, and that is said to be dispersion medium and dispersion phase. Dispersion medium and dispersion phase. So under colloids, now in the last part we need to study something called as dispersion medium and dispersion phase. Okay, students. Now, let me take the example of starch in water. Let me take the example of starch in water now. Let me take the example of starch in water. Let me say that we have a beaker. We have here the starch solution. This is said to be starch solution. Tell me, students, for a colloidal solution, what should be the particle size? The particle size should be ranging between 1 nanometer to 10 to the power of 3 nanometer, that is 1000 nanometer. So let me show some dots, so that would mean the starch particles. Let me show some small dots. Let me call it as a starch solution. Now you know that something should be called as a dispersion medium. So dispersion represents an intermediate mixture between the true solution. You know that what is dispersion? So dispersion of starch. So when I say use the word dispersion, what is the meaning of dispersion, students? It is an intermediate between, it is an intermediate between true solution and suspension. That's nothing but colloid suspension. When you say that you have prepared a colloid, a substance is said to be colloidal state if it acquires the particle size ranging between what? 1 nanometer to 10 to the power of 3 nanometer. Now, here to prepare this starch solution, we can call it as colloidal solution. We have used water. Water is called as dispersion medium. Students, what is that called as? Dispersion medium. Starch is called as dispersed phase. I think this point is clear, students. Now, can you tell me what is pink dot? Pink dot, let me call it as starch. Let me say water is represented like this. This is water. Now tell me what is starch? Starch is dispersed phase and H2O is said to be dispersion. H2O is called as dispersion medium and starch is called as dispersed phase. So what you have studied now is like this. Let me say colloidal dispersion is of two types. Colloidal dispersion is of two types. Means it is made up of two types. One is said to be dispersed phase, and another one is called as dispersion medium. So dispersed phase is analogous to solute in solutions. It is analogous. Analogous means what? Similar to. It is analogous to solute in the solution. So particles are being dispersed. Next, dispersion medium. So is analogous to. Dispersion medium is analogous to solvent in solutions. Now you should know that dispersed phase is not continuous. It is said to be a discontinuous phase. This is said to be discontinuous phase. discontinuous phase. And dispersion medium is said to be a continuous phase. This is said to be a continuous phase. So in our next class, students, we have to study the difference between the true solution, colloidal solution, and the suspensions. So please read all the things again, revise it, so that the next class will be easier. So what all things we have studied in today's class? We have completed the concept of catalysis. Under the concept of catalysis, we have studied lot of things: homogeneous, heterogeneous, differences between them. Then we have studied something about the enzyme catalysis and shape selective catalysis, then selectivity of a catalyst, and we have studied something about, after selectivity, we have studied activity of a catalyst, and we have studied the mechanism of heterogeneous catalysis. So then we have studied about the mechanism of enzyme catalysis. So all these things we have studied in today's class, student. And in the introduction of colloidal solution, so we have studied something about what are colloids. So I have given the brief introduction on the concept of what is said to be a true solution, what is said to be a colloidal solution, and what is said to be suspensions. And I have define two terms, like what is dispersed phase and what is dispersion medium, and what is said to be continuous and what is said to be discontinuous phase. And now we have to wind up the class for today, and tomorrow we'll continue with the comparative study of true solution, colloidal dispersion, that is colloidal system, and the suspension, then classification, methods of preparation of colloids, purification and its application, so that we can end the chapter of surface chemistry in next two classes. Thank you, students.